Hello people, in the previous video we saw an introduction to machine learning, what is machine learning, what are the types of machine learning, and later we saw that there are 4 types of machine learning, which are basically supervised learning and then unsupervised learning, self-supervised learning, and semi-supervised learning. Those people who haven't seen the previous video, I would highly recommend to go to the previous video and see that, because this is something that will lay down the foundation of everything we'll be discussing next. Then we deep dived into self-supervised learning, and in a brief introduction I told you what is linear regression and what is logistic regression, and also we got to know what exactly is the meaning of the term supervised, which was basically that we have value x, also we have value y, and for every value of x we have a value of y. That is, we have a complete pair of information to train a model. So that was it for the previous video. Now today we'll be talking about an in-depth into logistic regression. So logistic regression is one of the most used algorithms in supervised learning, and it is highly used. So okay, before going to logistic regression, it's more important to look into the linear regression part. So logistic regression we'll be looking into after linear regression. So let's talk about linear regression. So what is basically linear regression? So yesterday we saw, in the previous video we saw that using the house price prediction problem, that how we can fit a line into a test data. So let us draw that once. It's not. Second. Try this out. Yeah. So this was actually the price of the house, and this was the area of the house. Okay. Now there, let us put some values to it, and let us say that these are in thousands of dollars. So let us say this is $100,000, then this is $200,000, then 300, 400, and $500,000. So this is the price of the house in $100,000. Okay, sorry, $1K. So this is basically the value that we are talking about in the thousands of dollars. Now if we take the size of the house in square feet, let us say this is for 500 square feet, this is for 1000 square feet, this is for 1500 square feet, then 2000 square feet, and so on. Now let us put some values to it. So let's say the values, a value pair that we have, let us say this is the value pair that we are looking into. Okay, this is 1 point, then this is 1 point, this is 1 point, this is 1 point. Suppose this is 1 point, this is 1 point, this is 1 point. We are putting it arbitrary values. Okay, now after putting in arbitrary values, now you want to fit a line between these points. So let us say you fitted a line, this is the line you're fitting in. Okay, now in this line, if you see, this is the mapping that is happening. This is the fitting that is happening. Okay, so based on this particular line, how we are going to fit the data. So let us suppose we have this data points wherein we have the value of size. Once again, we have the data of size, and this is in square feet, and we have another data of price, which is in thousand of dollar. And so basically this is the x-axis, this is the y-axis, and these are the value that we have. So let us say the size of suppose 2104 feet, we have the price 460. Then 1416, we have the price 232. Then 1534, we have the price 315. Then for size 853, we have the price 178. Okay, so how are you going to, so let us talk about few of the notation, how we are going to mention all these values. So there is a certain notation that we follow in defining the data set. So what is the basic notation? So there are, suppose there are these are the total number of training examples. So these are known as M. So we denote number of training examples as N. Then the next notation that we have here, the X is denoted as input variable, or what we talked about previously, it is also known as features. Y is called as output variable and also known as target. Next is X comma Y. This is one training example. Then we have Xi comma Yi. This is basically the ith training example. So suppose we talk about this one. Okay, suppose we are talking about this one. This is here, this is the first training example. So we'll represent it as x1 y1 is equals to 2104 comma 460, right? So this is how you're going to represent it. As per this, the value of M, what do you think, what is the value of M? M is equals to M is equals to 4. Okay, now what else? X, Y we know, and all these values we already know. Okay, now what's the next thing? How do we represent it? That is one thing. So basically there's a flow that we define for this. For all the algorithm, there's a certain flow that we have. So this, what we do basically, I'm still learning how to use this. So there is a training set. Out of this training set, you select a learning algorithm. Here we have selected the learning algorithm as linear regression. Okay, so you select a learning algorithm. Then in that learning algorithm, there is a certain hypothesis. Using that hypothesis, you fit the algorithm. That is, what do? You provide an input. Here the input is size of house, and you train it such that this hypothesis that we have is trained so that it can give us an estimated price. Here the estimated price is denoted as y hat. Okay, that is basically this whole algorithm will basically map your x comma y. Okay, so this is how we do it. Now the questions comes, everything okay, we understand, everything is okay. How do we represent this h? Okay, how do we represent this h? So the basic explanation or the representation of x is h theta of x is equals to theta naught plus ka theta 1 times of x. Yet this h theta of x is nothing but the predicted value of x. Okay, so if this is your curve, and this was your fitting, suppose these were your fittings, these are your data points, and you made a fitting of linear regression as this, then the equation of this line is nothing but h of x is equals to theta naught plus theta 1 times of x. Okay, or h theta of x and h of x is same thing, because it is dependent on theta, that's why we are representing it as h theta of x. Okay, and we all know that regression algorithms are used to predict the real values. So here we'll be predicting the real values rather than discrete value as in the case of the classification algorithms. Okay, basically in this particular thing, what do you think, what are the trainable parameters? What are the parameters that you need to learn? So we all know that we have all the information regarding the x value and the y value. In order to find this equation of h theta of x, we have two parameters that we need to learn, which are theta naught, theta naught and theta 1. So these are basically our parameters, or also known as the learnable parameters, trainable parameters. Okay, so suppose we are given a training set and we want to train our algorithm so that it learns this theta naught and theta 1. How do you think how would you represent this whole algorithm such that in an iterative manner, when it goes through all this values of your x and y pair, how you're going to train your algorithm? So basically we want it that our algorithm at the end should choose the values of theta naught and theta 1 such that it best fits the data. Okay, so how do we do it? So in order to do this, there is a loss function or the cost function that we train so that it can learn it. It is known as the mean squared error. What is called? The mean squared error. Okay, how is it represented? Okay, so basically once you train this algorithm, we need to find the minima of theta naught comma theta 1. That is, you need to minimize a certain value in terms of theta naught and theta 1 such that this value, that is summation over all the data points, that is I equals to 1 up till L h theta of x, that is your predicted value, minus y, that is your actual value, whole square multiplied by 1 by 2m. This should be the minimum. So basically you have to determine the values of theta naught and theta 1 such that this complete value is minimum. That is how you train the algorithm. Here, what is the value of h theta of x? We saw It is nothing but theta naught plus theta 1 times of x. So you'll iterate over all the values of x from 1 till m, and you'll find this sum. This is not important. This is a regularization parameter. This is not a very important term. If you remove it, it's fine, but it's generally set to include. Okay, so using this, once you minimize this particular thing, then you should get a pair of values for theta naught and theta 1 for which this whole function is minimum. Okay, now let us see what is this known as. This function that we are minimizing, what do you think what is known as? It is basically called as cost function. That is, we have to minimize the cost of our algorithm basically on what values we are supposed to minimize it, on values theta naught and theta 1, because the values of x and the values of y, as we see previously in this whole equation, there are certain values which are fixed. That is, the value of x is as per the data set we have, the value of y is as per the data set we have, the value of m is the number of data point. All the values are same. So how you're going to minimize this? You can minimize it by selecting the values of theta naught and theta 1 for which this particular function is minimum. So that is why we say that cost function is j of theta naught comma theta 1. This is the representation which is equals to 1 divided by 2m summation of I equals to 1 up till m h theta of x of I minus y square. That is what you need to minimize. This is called as cost function, or also known as the mean squared error. Why do we put this half? We could have also done 1 by m. We put this half as a convenience for computing gradient descent, as derivative term of a squared function will cancel out the 1 by 2. So when you find you will find the derivative of this particular function in gradient descent algorithm that we'll be talking about later. This will basically cut this out, and we'll be left with 1 by m sigma equals to 1 to m h theta of x of I minus y. Okay, so if you remember, what is del d by dx or del by del x of x square? It's nothing but 2x. Now if you have 1 by 2 times of x square and you need to find the derivative of this function, it will be nothing but 2 into 1 by 2 times of x, which is nothing but x. Okay, so on the similar terms we have added this 1 by 2 value so that the gradient descent would become simpler, such that 1 by 2 terms get cancelled when we calculate the gradient descent. Okay, so that is it for a linear regression hypothesis. Now we go to the intuitions for the linear regression or the cost function. So for the cost function, we have two intuitions. Let us talk about intuition 1. Okay, here we have the hypothesis h theta of x is equals to theta naught plus theta 1 times of x. Okay, what are the parameters? The parameters are theta naught comma theta 1. Okay, what is the cost function? This is basically the cost function. Okay, and what is the goal? The whole goal of this algorithm. What is the goal? The goal is to minimize j theta naught comma theta 1 for such that on terms of, not here, theta naught or theta 1, we'll use these values of theta 1 such that the value, this is minimum. So this is our basic intuition. So let us take a simplified manner to it. let us take the initial value of theta naught to be 0. Okay, then what do you think? Our hypothesis will become h theta of x is equals to 0 plus theta 1 times of x, which is basically theta 1 times of x. How would you show this in a graph? Y is equals to mx will pass through the origin and it will be a line like this, wherein your slope is theta 1, right? So this is the basic intuition. If we consider that the bias value or the theta naught term is 0, then this is it. Now what would the cost function? The cost function j of theta will become, or j of theta 1 will become 1 by 2m sigma I equals to 1 up till m h theta of xi minus y square. Okay, now h theta of xi is nothing but theta 1 times of xi. Okay, and this is the term that we have to minimize. This is our whole goal, that is we need to minimize values of theta 1. We have to select a value of theta 1 such that this cost function is minimum. Okay, now let us explore this. Let us do a deep dive into this equation and how would you define the cost function. So let us say this is basically your h theta of x. This particular column represent h theta of x, and this is your cost function, that is j of theta or theta 1 here, because theta naught we are taking it as 0, and these both are for fixed value of theta 1. We'll see if we fix the value of theta 1, what are the changes that will happen. Okay, so let us say that these are the values that we have. Okay, this is the y-axis, this is the x-axis, and suppose theta 1 is equals to 1, then what will be the value? Then for value 1, when theta 1 is equals to 1, then y will equals to x, that is this will be a point 2, 2 and 3, 3. This will be a point, and this will be a kind of a straight line passing through all 3 points. Okay, this will be a line. Now if we calculate the cost function for this particular thing, then j of theta 1 will be 1 by 2m summation of I equals to 1 up till n h theta of xi minus y of I square. Okay, let us put the values. 1 by 2m sigma I equals to 1 up till 3 theta 1 of xi minus y I square. Okay, so we know theta 1 of xi for I equals to 1. What is theta 1? Theta 1 value is equals to 1. Then for I equals to 1, the value of theta 1, let us put as 1 by 2 into 3, which will become 6. Theta 1 for I equals to 1 will do, for theta 1 it will become 1 into x1 is 1, y1 is 1. This would become 0. Then for I equals to 2, it will become theta 1 1, x1 x2 theta 1 1 x2 equals to 2 minus y2 is equals to 2. This would also become 0. Then for y equals to 3, theta 1 1 x3 3 y3 3. This will also become 0. So all the values turn out to be 0. That is, this is the minimum cost function, or you can see the best fitting line for this data point. The equation of the best fitting line for this data point is actually y equals to x. Okay. Now we'll draw it. We'll put these values into this. Let us say we are going to draw how the cost function, the value of cost function changes. We'll be keep on varying the value of theta 1. Here we have taken the value of theta 1 is equals to 1. And this we are drawing the curve between, one second. Here we'll draw the curve between cost function and this will be j of theta 1 and theta 1. So we saw that for value 0, thus for value equals to 0, or this would be the value 0, and suppose let us say this is the value, suppose the value of theta 1, here we'll take 0.5, and here the value is 1, and then we take 1.5, and here we take the value of 2, and this is the value of cost function. Let us say 0 here, then 1, then 2, and then 3. We saw when we took the value of theta 1 to be 1, the value of cost function was 0. So this becomes your first data point. So let us draw it. So this is your first data point. Okay. Now let's move ahead and select some other value of theta 1. Okay. So here we'll take the value of theta 1 is equals to 0.5. Okay. Now if we take the value of theta 1 is equals to 0.5, how do you think? But the values of x and y are same. Okay. That is, the data set that we have will say x comma y values are 1 2 3 and 1 2 3, and here to took the value of theta 1 is equals to 0.5. Suppose you have this hypothesis, so let us draw it. So you have 1 2 3, and you have 1 2 and 3. So original data sets says that this is your data points and on the graph, but you kept the value of theta 1 is equals to you have taken at 0.5. So if you take the value of 0.5 in theta 1, it would become y is equals to 0.5 times of x. That is, when x is equals to 1, the value of y would be 0.5. So somewhere here, then you will take the value of x is equals to 2, then your value of y would be 1 somewhere here, and then when you take the x value is 3, it will become 1.5. It will be somewhere here. So if you draw this curve or this line, then you see it's off from the original values. By how much is it off? So this is the, you see, this is the distance, and this distance was actually 0 when you found the perfect fit for in the previous case, and that is where you saw that the cost function also turned out to be 0. That is, it is a perfect fit for your particular data set. Now here you took the value of theta 1 is equals to 0.5, and this is your predicted line. This is your hypothesis basically. This is your h theta 1 of x, and these are your original values. Now let us see what is the value of your cost function. So j of theta 1 is equals to, as we remember the equation, sigma equals to 1 up till m, and then let us put the values, or let us write the equation first. H theta xi minus y square. Okay, now let us put the value 1 by 2m, or let's directly mention here 1 by 6 and so this would be basically, I'll put the values. If you want, you need to calculate, you can put up the values and you will get the values. Okay, now if you find this value, it turns out to 1 by 6 times of 3.5, which is nothing but 0.58. So this is the cost function that you are getting if you select the value of 0.5. Now this was a previous graph. Okay, in this particular graph, this was a previous graph. Okay, let's copy it and here let us, one second, let us paste it here. So here previously you had the value for theta 1 value is equals to 0, you got the value of cost is equals to 0. Now for the value of theta 1, when you took the value of theta 1 to be 0.5, you get a cost function of 0.58. So let us say when you took this value of 0.5, so this is basically what you got. Okay, this is somewhere you got, and this was the value you got for when theta naught is equals to 1. Okay, now let us take another example. Here basically let us say that you have taken the value of theta 1 is equals to 0, and what does it make? It makes your y value, y is equals to theta 1 times of x will actually become 0, y equals to 0. Now when you plot this curve, you have the values of 1, 2 and 3 for x and 1, 2 and 3 for y, and these are your original data points, that is 1, 1, 2, 2, 3, 3. This was a best fit line for 1, 1, 2, 2, 3, 3. Now what you have mentioned, that this is your hypothesis, that this is your basic hypothesis for this particular data set. One second. So this is your hypothesis, that is basically nothing but y equals to 0. Okay, now if you check the distance between the original and the hypothesis, it is quite high, which mentions that your cost function should be high. Let us see the cost function. Now if you put all the values on the cost function, this is what you'll got. This is what you'll get: 1 square plus 2 square plus 3 square. Why will you get this? Your hypothesis says you have the value of 0, but actual value is 1. So 0 minus 1 square is equal to 1 square. 0 minus 2 square is equal to 2 square. 0 minus 3 square is equal to 3 square. And this comes out to be 2.3. Now if we put this value in our cost function curve, so it will come somewhere here. If you have taken the value of theta equals to 0, you are getting 2.3 somewhere here. Okay. Now what if you'll take the values of theta 1.5 to 2.5, you'll get a certain graph for the cost function. Let me see what kind of graph you'll be getting. Not here, it has to pass from here. This is the kind of graph that you're getting. Okay, this is called as parabolic curve. That is, this is the point of minima. Here you are getting the minimum value. This is the value of theta 1 that you have to determine, for which the value of your j theta 1 is minimum. This is a point of minima, and as you go either this side or either this side, that is, if you even reduce the value of theta 1 or you increase the value of theta 1, anyhow the value of or the cost function would increase. Okay, understood? This is the hypothesis that we got, that there is a certain value of theta 1 that you have to determine, for which the cost function is minimum. So that is how it happens. Your algorithm basically have to iterate over all the pairs of values of theta 1, and it has to determine which is the value of theta 1 such that the cost function is minimum. Now you understand, if you provide a certain data set, how would your algorithm determine the best fitting line? So in order to determine the best fitting line, the equation of your best fitting line, what is the value, or what is the equation? Y is equal to theta 1 theta naught plus theta 1 times of x. It has to iterate over all the values of theta naught and theta 1 such that it will minimize j theta naught theta 1, and for whatever values of theta naught comma theta 1, it will get the minimum cost function. It will basically take those values of theta naught and theta 1 and mention this hypothesis, and this is for the linear regression. Okay, now we'll also see what if we make it two-dimensional. So once we make it two-dimensional, it will become a bit of complex. Let us try and explain it. Okay, suppose this is a cost function j theta naught comma theta 1, and here we have the hypothesis as y theta naught plus theta 1 times of x. Okay, this is our hypothesis, and let us say let us one second. And now we'll take suppose this is our data set. This is our data set. We are putting any random points here. So first value of theta naught that it determined, suppose on that first value it has taken the value of theta naught and theta 1 such that your hypothesis is this line. This is your hypothesis for first set of values of theta naught and theta 1. Let us assume that. Okay, this is your hypothesis, and let us put some value to it. Suppose here you have taken the value of theta naught is equals to 800 and theta 1 is equals to 1.15, that too minus 1.15. So this is your first set of values that you selected. Now you go ahead and you select another set of values of theta naught and theta 1, and this will select one more values of theta naught and theta 1, and suppose this we have the same data points. That might not look like similar here, but let us assume these are same, and here also you have the same set of data points. And this time you selected a value of theta naught and theta 1 such that you tilted a bit and you made it somewhere like this. And for this one you selected the hypothesis such that at the end you got the perfect fit. So here let us say the values of theta naught you selected was 30 and theta 1 you selected was 0, and here the value here whatever you have selected is the best fitting line. Okay, now if you draw a curve and here you put the values of basically theta naught comma theta 1, and when you draw the curve in order to for the respective cost function, and let us assume this is where the cost function is 0, then as you go up it will keep on increasing by 0.1, 0.2, 0.3, 0.4, and as you go down it will increase. Because cost function is always positive, so let us say it's minus cost function, but it is never minus. It is basically always positive because it's a squared value. Okay, now let us see. Let's check the values. This is minus 1000, minus 500, 0, 500, 1000, 1500, and let us say 2000. Okay, now here we'll plot the curve. So the first point that we have is with 800 and minus that we took was 800 and sorry, I did a mistake. This is not a cost function. Basically this we are showing as this is basically theta naught and this is theta 1. Okay, and we'll be showing the cost function, plotting the cost function on the graph. So for the first set that we have, for which we had theta naught was 800 and theta 1 was minus 1.15, which will be somewhere here. Okay, now in the next case we had theta naught is equal to 30 and theta 1 was 0. Let's take it according to the graph that we have. Let's make it 310. So for this you had the value 310 and here you had 0. This is the point that you get. Okay, and for the last curve you had the minimum value, that is you got the best fit. Now when you draw the hypothesis, what is the hypothesis? j of theta naught comma theta 1 is equals to 1 by 2m times of h theta of x minus y square. This is a square equation. Okay, so that basically this is a two-dimensional equation. So when you will draw it on a curve, this will basically the kind of curve that is shown this like this. It is not actually like this, it is actually a curve like this, and these are the points that we are looking at the 2D phase. These are the points. It is like a bowl shape, and we drew it on the two-dimensional space. This is how it looks, but in the three-dimensional space it will look like a bowl shape, or as like this, a cup shape kind of a structure will be seen. So when you look it from this angle, this particular angle, from top bottom, when you look it, then how would you see? And what are these lines? These lines are basically the lines for which the value of the cost function is same. Okay, for this particular line, you see this is the curve for which the value of theta naught, the value of theta naught and theta 1 would change, but the cost function will remain same. So let us draw it over here. When you look at top bottom and try to draw it, just I can draw. So suppose this was the point where you got the minimum, and then from there on it will keep on increasing. So you see there's a distance is large, but you assume that this is having equal distance. So you see this is the direction, that is this is the minimum point where you're supposed to reach. So here this particular curve, you have a certain value of theta naught and theta 1 such that you reach this minimum point, and that is, as you are going from this point to this point, you are going towards the minimum. That is, if you assume it as a slope, the slope is downward here. That is, you have to go in a direction such that you meet the minimum point. So this is how you select the values of theta 1 and theta 2 such that you move towards the minimum point. That is, you don't take the first point. You might have for the first set of values of theta naught and theta 1, you'll select some random value, and then you'll check, are you moving towards the minima? Is your gradient downwards and going towards the minima? If yes, then you are going in the right direction. If no, then you have to take some other set of values such that you go towards the minimum value, and you find the best set of values of theta naught and theta 1 such that your cost function will become minimum. Okay, so that's all for today. We have learned about what is linear regression, how do you represent it, how the machine understands your data point, how it tries to find the best set of values of your parameters such that it fits the linear algorithm or linear regression equation in the best possible way. At the end, we talked about that there is a way called gradient descent. The circles that you see is a gradient descent such that you have to move towards the minimum point so to get the best values of theta naught and theta 1. If as of now you're not able to understand this particular, the last part of today, the gradient descent part, how you're moving down, how you're determining the value of theta 1, theta naught and theta 1, no need to worry. If you have overall understanding of the hypothesis, how you are fitting the equation, how you're determining the cost function, that is fine. In the next session we'll be talking about gradient descent in detail, and we'll find out how is that this convergence actually happen, how with every iteration you determine whether you are going towards the converging point, whether your gradient is or the slope of j theta is going down or not, and if not what you do, and if yes what you do, how you move your step, and how you select the values of theta naught and theta 1 with every passing iteration. So that is what we'll talk about, a greater detail of gradient descent, and this is something that is common in most of the algorithms or machine learning algorithms. The best fit is tried to find out by going to the minima of the cost function, and this is the cost function. You have to find the minimum values such that you can find the best fit of your data points. So that is all for today. Tomorrow we'll get into the gradient descent. Until then, best of luck, have fun, and those who have not liked the video, please like it, subscribe the channel, let your friends know that there's a channel which is talking about machine learning in depth, and thank you for your time. Bye bye.